Good morning, everyone. For those that don't know me, I'm Luke Wyles. I'm a program head at Analysys Mason. That means I focus on a specific area of research, in my case, space ground segment. Though recently I've been doing a lot more work on the military communications side of things, so I felt this conference and presentation would be a good way to intersect those topics. For those of you that don't know us, Analysys Mason is a technology, media, and tech consultancy and research house that several years ago bought out the space consultancy NSR and melded that into our team. So now we have a sort of, I think, quite unique positioning that melds telco and space insights at a time when that's quite pertinent. Just to introduce the topic today, I think this has probably been quite a belabored point this weekend, but ground resilience certainly defines operational outcomes. As we were just hearing, it's sort of more crucial than ever for frontline communications, and can be the first point of failure in a SATCOM network during conflict. There's, of course, the famous KA-SAT, Viasat case study where maybe 30,000 user modems in Ukraine were disconnected through an electronic warfare attack. And this really demonstrates how fundamental resilience is to maximizing growing and complex space segment. The number of satellites is only accelerating, the variance in their orbits, and the potential combinations of services you might be attempting to deliver on the ground and that need complicated orchestration and management. For today's sort of conversation, I wanted to sort of segment it by sort of three temporal eras, which might each have several sort of crucial technologies that the SATCOM industry is thinking about and that we need to attend to on the ground. The first of those being hardware and hybridization, the sort of progress towards a multi-domain, multi-network environment has to start with equipment that can handle those things. So we'll address multi-orbit terminals, deployable gateways, and in the context of military comms, the necessity for zero trust frameworks, which are all the buzz at the moment. Then next, we'll go on to software-defined automation, uncovering the adoption of cloud-integrated ground services. Again, that's going to be an area where governments lead the way on the commercial sector, looking at multi-domain orchestration to connect even disparately owned space assets and edge devices, and finally the sort of appearance of AI-driven operations. The last section, I should hope, doesn't devolve too much into outright sci-fi, but it's going to be focusing on first hybrid RF and optical, and then quantum key distribution as a key, please forgive the pun, as a key enabler of resiliency. So we'll start with this first era and kick off with multi-orbit terminals. There's been a lot of buzz in recent years in the SATCOM world about multi-orbit being the sort of linchpin of resilient connectivity, and that's certainly the case for the short to medium term and in the government sector, which is going to be driving a lot of these demands, as I'll surely reiterate several times. The premise, again, quite a well-worked point, but you could enable handover within a LEO constellation or onto a GEO-link, whichever is available. The early terminals do this sort of via switching in the order of tens of milliseconds, but the sort of more cutting-edge flat panel antennas and other devices can connect to multiple orbits simultaneously. That requires multiple concurrent modems, which at the moment is difficult to achieve over sort of shared compute, so there'll be separate physical modems, and that drives a big swap-C difficulty. The same can be said for if you're doing a flat panel array that has both a GEO and a LEO segment. The GEO might be running a much smaller portion of the traffic than the space of the terminal which it occupies. So it's generally going to be those verticals, those use cases, particularly military, which most need the sort of zero-fail connectivity, and we'll be happy to pay for that as compared to more consumer-facing or enterprise segments. Some equipment vendors and service providers are already working in the multi-orbit space. There's a bit of a disparity between some of the approaches, where some approaches use just combined multi-orbit single terminal, which is really key for more swap-constrained verticals like aero, but in the maritime world, we just see players like Inmarsat melding together several different terminals and channel bonding them to have a unified SD-WAN sort of network management, but having procured the terminals from different providers. So it really depends on the use case. Your mileage may vary between a mono or multi-terminal service. The next section, deployable gateways. This is another thing which is being pushed quite heavily by both ESA and the Space Force, where they want to be able to not only bring down the deployment time for out in the field gateways, but also to have them be much more mobile and to allow forces to reestablish local SATCOM base in the event of sort of main regional hub being put down due to jamming or some other EW attack. Some of the key programs I mentioned, there's the Space Force Rapidly Deployable Ground Entry Project or program, the US Army GATE program, and the ESA Optical Nucleus, which is trying to develop highly mobile optical gateways, although that's, I think, not even scheduled for testing until 2027. We'll come on to optical later on. Several players are trying to make progress in this space, whether it be a really software-defined approach that Kratos is pursuing with containerized edge applications, or the deployable Skynet unit Airbus is working on, or integration with a commercial, like AWS ground station. You can sort of see the vision, though, is from these various programs, like from the US Army and ESA, they want to bring down the speed of setup to 12 to 24 hours, inclusive of equipment deployment. So really, you want the actual network joining to be as intent-driven and hands-free as possible. The third sort of big trend in this first era is zero trust and cryptography modernization. These kind of go really hand in hand, but the sort of zero trust frameworks that the DoD and allies are pushing are trying to pursue automated networks that continuously check that every device is certified and authorized. And in the sort of DoD's latest publications, they've been saying that by 2029, 2030, all future and even like existing networks need to be following these protocols. PQC, that stands for post-quantum cryptography. Kind of sounds a bit weird here to bring that in early in the presentation when we're going to get to quantum later, but I suppose the thinking goes that if quantum computers will be developed such that can break contemporary cryptography algorithms like RSA, ECC, then you'd need to develop a quantum-resistant cryptography ahead of time to prevent your data being tapped retroactively down the line. So the new protocols set up by NIST is a quantum-safe cryptography protocol which uses some, I guess, more complicated math, some lattice-based math to develop shared keys and codes. It's ready, it's been set in stone, but now it needs to sort of enter an adoption phase. So in the sort of past few years, we've seen zero trust frameworks go through doctrines and pilots, and likewise the cryptography standards for post-quantum resistant crypto have also been finalized by NIST, NSA. And the reason I'm stressing this area here in this sort of era one stage is because the main sort of precursor to eventual quantum grade security is going to require a hybrid adoption period. Sort of in the intervening period, you would want your terminals, your equipment to run dual stacks of both existing classical algorithms and quantum resistant algorithms. But you would retain the classical in the event that the other device you're talking to doesn't have the PQC or, for some reason it's otherwise not available. Going through into sort of 2028 and 2031, a lot of these pilot programs and hybrid programs will become doctrine and become embedded in allied orchestration pools. So the onus is on players, security players, to act now and start to develop these dual stack pilots. Like, for example, you could use the ECDH classic algorithm and then the Kyber PQC algorithm, which is the NIST's way of establishing a key exchange in a quantum resistant manner. Just to sum up era one here, We've got sort of takeaways and focus areas for each of those three technologies. In the multi-network terminals area, the hardware exists, but it's very swap-C constrained. Open APIs and waveform magnetic control would be really key to bring about the modem swappability piece. But I think it needs to be understood that the value proposition of these terminals is ultimately a multi-network one. I think come the 2030s, the perceived value of having a GEO and LEO sort of combined system might be, it might require too bulky and too expensive terminals as compared to just a multi-LEO system. So in the future environment where there are more LEOs available, more open to play LEOs available, then I think it makes sense to have LEO only but still multi-network terminals. So some of the more expensive multi-orbit terminals currently, I think, will position themselves out of future markets where really the customer just wants multi-network, whether it's in different orbits or not. For deployable gateways, they currently have manual configuration and power dependence. These are the big limiters. So firstly, need to standardize modular interfaces and have zero trust credentialed boot up. That means that the gateway itself can remotely boot itself up onto the network, but does so in such a way where the network is still checking that it's trusted and will continuously check that it's trusted. Finally, on the zero trust frameworks and post-quantum cryptography, as I said, the onus is on enabling a dual stack approach through 2027, 2028, and getting onto common allied zero trust schema. You'll see here I've referenced the FMN Spiral 5. These spirals are sort of the iterative layers of network intelligence that the US DoD expects to procure and support. So Spiral 5 loosely aligns with the 2025 to 2027 period, and then go to Spiral 6, and Spiral 7 is the latest scoped one, which loosely lines up with our latest section. I'll keep trying to move forward here, kind of conscious of time, but we'll get into the next era, which is software-defined automation, and the big one everyone brings up immediately is always cloud-integrated ground segment. There's been a lot of progress on that. The Diffie consortium is working on, or has worked on and delivered interoperable IP to replace IF, to replace IF through a digitalized IF. And their new standard, the Diffie 2.0, introduces DiffySec, which is really crucial for government players because it comes with a bunch of additional securities related to zero trust checking and other approaches like that. Kratos, as I mentioned, they're probably the hub provider most pursuing software-defined and containerized applications. They hope to provide as-a-service waveform processing from 2026, and likewise, AWS Ground Station is looking to develop from a current sort of quite siloed approach between ASGov and ground stations and have these become more integrated, likely through the development of the Kuiper constellation. The drivers, I think, are probably quite well worked on this point, but just to run through them, operational agility, flexible OpEx cost structure that aligns quite a lot with how a lot of MODs have been discussing their approach to SATCOM as wanting to be more strategic and short-termist and not have to make huge CapEx investments in data infrastructure in this case. And so being able to tap into cloud infrastructure by OpEx seems certainly advantageous. But yeah, it's really the elasticity and the federation of operations all across the network that can be sort of scaled up or down unilaterally within the cloud. But there are challenges. There's accreditation of different cloud providers and whether governments would be inclined to trust them. And then limited interoperability, as much as standards like Diffie and MEF are trying to pursue interoperability across different layers of the protocol stack, it's far from complete, and indeed there's an incentive for different cloud providers and software providers to tailor their solutions to be interoperable on paper, but to really work best with their own systems. There's been a similar kind of trend to that in the telco O-RAN space, where O-RAN is sort of labored to present the same value proposition as a proprietary full stack from, say, Ericsson. The cloud pricing and backhaul dependency, again, there's not so much of an incentive for AWS to make cloud and the same for Azure to make cloud cheap for everybody else. People run into egress pricing. You'll hear that as a big complaint for anytime you leave an AWS cloud zone. Excuse me. So there are definitely some challenges here with cloud integrated ground segment, but once again, it's governments that are leading the way because it's governments that want the most autonomy in reordering their networks and doing so at a whim. Next, for multi-domain orchestration, I've kind of got a fairly back of the napkin sketch on the right here, but the sort of premise is gateway, space, and edge all communicate with a central mission orchestrator and do so over zero trust boundary lines. So they're constantly, rather than having a single, like once in a lifetime authorization, they're constantly reauthorized to be interacting with the orchestrator and therefore with the other areas of the space, gateway, or edge. But I guess the whole premise of these zero trust boundary lines is to ensure that, or to facilitate the idea that you would procure space, gateway, and edge segments from different vendors. The benefits for sort of resource orchestration, RF resource orchestration, is to maximize those resources across a really complex space segment. The endeavor to coordinate a mesh of interconnected satellites is extremely complicated, and when they have steerable spot beams, there's a huge efficiency gain to be made with mobility. Having a narrow beam that just tracks the vessel precisely rather than having to have a chain of beams that lead out in front of its flight path. So, with the advent of software-defined satellites in GEO and ever larger non-GEO meshes, there's a real need to automate this like data policies. Likewise, we see players like Netcracker from the telco world developing their OSS and BSS services to then come and integrate those into resource controllers. Like, for example, the Lightspeed constellation has Netcracker providing the OSS, BSS, then they have Illyria as a Google spin-off doing their resource orchestration. And so there is still a lot of specificity and relationship contingency where these constellations have to establish quite early their vendors for these software capabilities, but through the adoption of open API standards, including like Illyria's federation APIs, you might expect through the 2030s to have these sorts of orchestration approach be more vendor agnostic. And I'm whistling through here because I'm quite conscious of time, but now onto AI Ops, the sort of final section for this era 2. We have some earlier AI applications currently available or in development, time series forecasting. That's not really a new thing. The resource orchestration piece is being developed in the context of like a mesh network. So for example, that Illyria case is not going to be validated in orbit until 2027, but it supposedly goes beyond normal machine learning and would use a deep reinforcement learning where it constantly checks the performance of the day's network against other regions and against other periods. I mentioned integrating OSS BSS, and some Gen AI and machine learning have been used there to construct and then efficiently price intent-based services. So that sort of removes the human element from setting up new complicated contracts. Onto the right side of the screen, the artificial intelligence will become much more embedded in the operations layer through 2029, 2030, some of that through the pursuit of 6G and terrestrial mobile, or just in mobile networks, which would seek to be an AI-native technology. And partly also is the development of the MCP, which is a model-agnostic control protocol being developed by OpenAI, which should really overcome a lot of the current difficulties in aligning API structures between different vendors. So the model control protocol endeavors to essentially do the working out for you of matching up these APIs. But yeah, the foundations are being set now, and then through 28, 29, there'll be scaling and the operationalization of these capabilities, and then maturation through 2030. Just some sort of key takeaways for the cloud integrated ground segment. They need to develop cross-domain orchestration gateways and standardized protocols. I mentioned Diffie-Sec, maybe OpenTelemetry as well, but there are still sort of swathes of the cloud piece that aren't standardized at all and that are more like vendor-specific. In the multi-domain orchestration, I mentioned intent-based capabilities. And it really requires new systems, new space gateway edge systems to expose their northbound APIs, some standard set of APIs for telemetry and RF control to centralized orchestrators. And again, on the AI ops and assurance, the assurance layer from an AI sort of remote diagnostics and like active healing approach would need to be built with the same hybrid PQC controls that we discussed in Era 1. Finally, to the science fiction. Hybrid and RF optical ground is section 1, and you'll see we have a nice forecast on the right for space-to-ground, ground-to-space optical terminals. Currently, these face quite significant technical challenges: atmospheric resilience, standardization, form factor. But this dramatic ramp-up, I mean, almost 100x in sort of 9 years, is, I think, justifiable in the context of ISLs and the fact that optical technology, space-grade optical, is being developed coincidentally for space-to-space connectivity, and it's an extra step. It's not the entire step to go from 6 to 582 just of the ground industry of itself. But Earth observation has kind of led the way here because of the lower frequency bands they're in and the fact that they need to dump a day's data in a short pass. They've really been relying on optical links. And now we see some standards coming from international consortium like CCSDS for O3K, that means over 3 kilometer optical, and then HPE standards is a high proton efficiency optical, which is the more sort of military inclined one, where they're trying to get the maximal effect out of a very narrow, hard to spot, low pulse optical beam. But yeah, essentially the premise is that ground-based orchestrator can swap between the optical or the RF, depending on what's available, and permit the satellite to use way more of its RF for user beams rather than for gateway. Finally, on the sort of Era 3 side, there's quantum key distribution, quite a fancy name, but it's going to be an overlay on the existing progress made in Era 1 and Era 2 on zero trust frameworks and post-quantum like cryptography, where the satellite layer will overlay the existing network and essentially provide disparate ground stations, or the ground station and the edge device, with a split pair of entangled photons, which over time will iteratively create a shared, physically but randomly determined key that those two devices essentially can continuously compare against to check that the other is still trusted, and to be able to see whether anything's interfered with, because it's quantum, so it will change state if observed or interfered with. So even if PQC algorithms are broken via like unforeseen high compute attacks, a QKD-backed link would retain a physical layer secrecy that currently isn't available even in those PQC algorithms. The final set of takeaways, both these areas are very immature, and I always feel a bit remiss like giving recommendations, but the key with optical is having a predictive orchestration that anticipates the atmosphere situation in a few moments' time and can coordinate the right adjustment in RF and swapping over to the lower capacity links. Similarly in QKD, it's the same advice of the hybrid crypto posture from Era 1, and QKD is really intrinsically linked to optical because these entangled photons are spread over optical links, so you'd need very site-diverse optical gateways with integrated like hardware security, firmware-coded security that can assure that even those received sites are still trusted. That's all for my presentation. I hope that's going to provide a nice springboard for the panel coming up. Thank you.